Hello everyone, my name is Lee. I'm a PhD student at the University of North Carolina at Chapel Hill. In this talk, I will present our IPSN 2021 work, Deep Functional Network, DFN, Functional Interpretation of Deep Neural Networks for Intelligent Sensing Systems. Let me first introduce the problem and motivation of this work. So today, the functional networks, DNNs, have enabled superior performance on many machine learning problems, and they have started to run on many intelligent embedded sensing systems, such as smartphones, autonomous vehicles, robots, smart devices, and so on. While these DNNs can provide excellent prediction accuracy on many intelligent tasks, they have some unique characteristics that are different from many other conventional computer programs. First, their lack of decomposability into intuitive and understandable components makes them black box and hard to interpret. Although many existing work, such as the surrogate model, model distillation, or feature importance algorithm, have tried to interpret and understand DNNs, they still remain as black boxes in most cases. And second, DNNs are monolithic and undecomposable, which makes it difficult to debug with the conventional programming tools and practices. Debugging a DNN in order to find out what went wrong is difficult, since they cannot be explained in many cases. And lastly, many state-of-the-art DNNs require enormous computing resources, such as a large size of memory and high-end computing processors, such as multi-core CPUs or GPUs. So, the goal of our work is to find out the internal workings of DNNs by decomposing a uniformly structured DNN into a high-level and human-understandable components, which can be better optimized to run on many resource-constrained, intelligent embedded systems. Specifically, we want to provide the description of the internal workings of the DNN and better programmability and better resource efficiency. The main reason behind this goal is that DNNs are usually designed as a network of uniformly structured neurons, where the high-level semantics of which subset of neurons is doing what semantic operation is not traceable. Instead, we look for an alternative design of deep neural networks where the network architecture is modular and human understandable, which is different from the traditional network of similar structured DNNs. To achieve this goal, we propose Deep Functional Network, DFN. So in this work, we propose Deep Functional Network, DFN in short, that translates a DNN into general programming code such as C or Python, consisting of high-level and human-understandable functions. A DFN is represented in the form of a directed acyclic graph DAG based on a functional programming paradigm, which interprets a DNN as a tree consisting of a set of functions, vertices, and their connections, edges. This figure shows the proposed DFN in which a DNN is first interpreted into a DFN with four well-known functions, that is FFT, convolution average cosine, and then it is converted into an executable programming code on the target embedded system. Let me explain how a DFN is generated from a DNN. The procedure of DFN generation from a DNN requires two steps. The first step is function estimation, and the second step is network formation. First, given a source DNN we want to convert into a DFN, the function estimation step tries to anticipate which functions are likely to be used in the DFN by estimating the function distribution. And next, given the function distribution, the network formation step forms a DFN graph, which is in the form of DAC by finding the network structure of the DFN consisting of final functions and their connections. And finally, the DFN graph is converted into an executable program code. The first step of DFN generation is function estimation. When we want to convert the source DNN into a DFN, there exist so many possible combinations of functions that can be used in the DFN. But unfortunately, we do not know exactly which functions should be included in the DFN. In order to solve this problem, the function estimation step estimates the likelihood of functions to be used in the final solution DFN in the form of their distribution. So by having the function distribution in which a function with higher distribution is more likely to be included in the solution DFN, while a function with lower distribution is less likely to be included in the DFN, we can probabilistically determine which functions are better to be used in the DFN. Then, the natural question here is how to estimate the function distribution. To this end, we propose function distribution estimator, FDE in short, which is a special designed DNN that estimates a distribution over the candidate functions expected to be present in the solution DFN. The architecture of FDE consists of an input layer, embedding layer, and hidden layer, and the output layer. The input layer separately takes the end-to-end input-output pairs from the source DNN, which is passed to the next embedding layer. And then the embedding layer projects the raw input and output data of the source DNN onto an embedding space where the dimensionality of data is reduced. And so the hidden layers combine the input and output embeddings and then make inference on the distribution of each function by learning the mathematical relationship between the two embeddings. And finally, the last output layer consisting of sigmoid vertices corresponding to individual functions provides the final function distribution. FDE is designed and trained to predict how likely a function contributes to the computation of the output when an input is given based on mathematical inference learned from the hidden pattern between input-output pair and the function. The second step of DFN generation is network formation, which defines the network structure of the solution DFN. Given the function distribution obtained from the previous function estimation step. So this step consists of two sub-steps. The first sub-step is network architecture search that finalizes the functions to be used in the DFN and their connections. And the second step is edgeway search that optimizes the weights of the edges on the DFN. Let's take a look at each sub-step in more detail. In the network architecture search step, the network structure of the final solution DFN, including vertices and edges of the DAC graph, is searched by using Cartesian genetic programming. So we use Cartesian genetic programming, CGP in short, for network search, which explores the space of functional programs involving the probabilistic selection of the fittest solution to the source DNN based on the estimated function distribution. So it iteratively searches for the fittest solution using a subset of functions based on the mutation of the current solutions by changing the functions and their connections. So finally, the DFN with the minimum fitness error is chosen as the final solution, DFN. So here, the fitness error is defined as the difference between the output of the source DNN and the DFN given the same input. So by minimizing this fitness error, the generated DFN can provide more similar outputs to the source DNN given the same input, which makes the functionality of the converted DFN as same as the source DNN. Next, once finalizing the network architecture, the next step becomes an edge-away search that optimizes the weights of the edges in order to further minimize the fitness error. When searching for the network architecture, at the previous step, the weights of edges are all set to constant. However, after the network architecture becomes fixed, the edge weights are adjusted by using the backpropagation algorithm in the same way to the DNN training, traditional DNN training, so that the DFN can be optimized to behave more similarly to the source DNN. And next, let's take a look at the evaluation result. So first, in order to evaluate the feasibility of the DFN, we converted 12 state-of-the-art DNNs into DFNs. So here, IR denotes interpretability ratio, which means that how many neurons of DNNs are converted into functions in the DFN, where 1.0 means all the neurons are successfully converted into functions. And fitness, here is the fitness error I explained on the previous slides. And accuracy is the prediction accuracy of DFN and DNN. And size denotes the number of functions used in the DFN. So this result shows that many state-of-the-art can be successfully converted into DFNs. They can almost equivalently solve many machine learning problems with comparable performance. Here are some examples of DFNs. First example is Inception architecture with Cipher10 dataset. And next example is a mobile net architecture with Urban Sound 8K dataset. So here in the DFN graph, the blue box denotes the functions, and arrows between functions denotes their connections. We also conducted application evaluation with a mobile robot. In this evaluation, we implemented a mobile robot that detects obstacles in the camera images and navigates itself with 4 actions according to the location of the obstacles. That is turn left, turn right, forward, and stop. And originally, the object detection and the navigation action selection are performed by AlexNet DNN. So here we converted the Alex DNN into the DFN and put the converted DFN on the mobile robot in order to perform the same task. And the result shows that the DFN provides comparable prediction accuracy, smaller memory usage, and fast execution time. The right side figures illustrate the DFN from the AlexNet DNN, which consists of 6 functions, which performs the object detection and navigation action selection task with only 0.8% of low prediction accuracy, with 2 times faster execution time and 766 times of less memory usage. And the last thing I will share with you is the limitation of this work. First, finding the DFN from a DNN is not easy. It is difficult to generate an optimal or near optimal DFN from a DNN due to enormous searching space. A second limitation is that finding the right functions to be used in the DFN given a source DNN has not been solved yet, even though the choice of functions has a significant impact on the generation of DFN. A last limitation is that it is challenging to derive consistent solution DFNs when converting the same DNN. Every time we convert the same DNN into a DFN, the network structures of each DFN are likely to be different from each other due to the nature of genetic programming algorithm. Thank you so much.